Now, what would be the other considerations for the Martian colony population size? 1 million is a fairly arbitrary number. Are there any other data points we can consider? If you look at the available data and our current estimate of the minimal viable population for the terrestrial vertebrates is around 4,200. That's probably the absolute minimal number required to maintain genetic diversity. But is there any other data points we can use? If we look at the states on Earth and cities, the smallest independent states is the island nation of Tuvalu. Its population as of 2023 is around 11,400. So that gives us the first possible estimate on how small our Martian colony can get. But using the smallest possible state is probably not the best example. There are bigger small nations like nation of Monaco, which is around 36,000 people. And there are also independent, more self-sufficient island nations like Iceland and Malta, roughly at 400,000 and over 500,000. So that gives us like the upper and lower range, what we can use for sizing our Martian colony to be sufficiently independent and self-supporting. There is also one other source of data. That's the number of total different occupations in the United States. And as of now, this number is around 830. Now, if you have one of each occupation, be it a doctor, lawyer, engineer, and a nurse, it's too much of a vulnerability to lose your only doctor on Mars. So you need some redundancy. If you have 10 doctors and 10 engineers, then you are a lot more robust. But there's also the thing of maintaining the knowledge and the skill. And if all your doctors or engineers are busy working, they will not have enough spare people to transfer their skills to the new generations. That's why if you look at something like 100 of them, you can always allocate 10% or 20% purely to the teaching duties. Now, that's another two estimates. If we multiply the number of possible occupations by 10 or by 100, we get 8.3 thousand and 83,000 as number of people. Now you can see a certain pattern is emerging where, say, a few thousand are too small of a number, and 500,000 would be good to get, but it's difficult. Even less than 1 million, 500,000 is a difficult target to reach. So somewhere around 50,000 and up, the self-sufficiency may reach the necessary level. There is one more data point, which is the city of Kingston, Ontario. Its population is over 100,000 people, and it has its own university, hospitals, shopping centers. In its own way, it's another estimate. If we built a city on Mars with a population of 100,000, we can expect most of the structures in institutions to have enough people to staff them. So that's the conclusion. How large would be the Martian colony? Good if we can get 500,000. Million is even better, but anything more than 50,000, and I think our foundation would be strong enough for the Martian colony to endure and persist beyond just first generation. Radiation is a known danger in space, so let me tell a little bit more why it is a big challenge and why it is different from the radiation sources on the ground. So on the ground, we have plenty of radioactive materials within the nuclear industry and other parties that work with them. However, most of the materials we're using or radioactive waste we have to deal with emit alpha, beta, gamma radiation and neutrons. However, the energy of those particles is not that high. What do I mean? What does it mean exactly? It means that the shielding for alpha can be very thin, and beta radiation sources like cesium or strontium can be also defended against with relatively thin shielding. Of course, gamma is more penetrating, but heavier metals can be used to shield against that, and water is a very good shielding against all sources of radiation. The second thing is the sources themselves are usually fixed in one location, be it nuclear power station or spent fuel pools, and it's relatively easy to build the shielding as thick as you need. On submarines, there are also quite a lot of mass available for the shielding, and water around them provides additional protection. In space, things are considerably different. Radiation is everywhere, and while it is pretty much the same type, like charged beta, protons and electrons, gamma and neutrons from the sun, the energies of those particles is much higher, can be orders of magnitude higher, and therefore they penetrate the shielding a lot deeper, and we need a lot more thicker shielding to protect against them. Additionally, high energy beta creates secondary radiation that can make actually things worse if you use any kind of heavy metals for the shielding. And big problem is mass budget is very limited for any spacecraft or space station. Every gram matters, and we cannot spend a lot of that on building meters of shielding as we can do on our planet. However, things are actually not as bad, meaning that we can design the shielding against radiation in space that's thick enough to remove any immediate danger. It will, however, present some additional health risks. So if you look at the chart, you can see the 4 major lines, and the topmost one is radiation exposure for a human in the relatively thin shielded spacecraft like Apollo during the solar flare. They will get a radiation dosage of over lethal threshold over 5 sieverts, so 500 rams, and that absolutely will kill you, and your death will not be pleasant. However, at the same time, with just a little bit of heavier shielding, think radiation shelter inside the bigger spacecraft, the dosage for the solar flare will be reduced to the much lower one that will not present immediate danger to your health. It will, however, present an additional risk of cancer and other potential health impacts, but not immediate ones. That's for the solar flares. Now for the other major source of radiation, which is the constant background, it's actually not that high, and you don't need like a heavy shielding to reduce it. However, it's very difficult to reduce the constant galactic background to the level that's the same for the low Earth orbit. You can see the difference in shielding, that 3 orders of magnitude more shielding only reduces it by so much. Water and aluminum can be used for this type of protection, and if combined together, our spacecraft crew on the trip to Mars, as well as any orbital colonists, will be defended against the immediate dangers of acute radiation sickness. However, they have to find a way to deal with the long-term effects of increased radiation. So the short answer, we can absolutely reduce the radiation, so it will not be an immediate death threat to our Martian colonists. However, it will be an additional risk factor for anyone visiting Mars or anyone living there full time. I want to talk about artificial gravity and why it is an important technology. So right now we know that Microgravity is a very significant health concern for any astronauts in space who live long enough. They will experience progressive deterioration in their health. Now, what we don't know is what's the lowest possible level of gravity where health of the astronauts will be not impacted. We also don't know what's the impact of the partial gravity that is below Earth level on the second and later generations of people growing in these conditions. We don't know what's the impact on development of the children, on pregnancies, and so on. There is some data on the microgravity in microgravity environment, but pretty much none on anything in between full gravity and zero gravity. That's why it is a risk factor that you want to solve before the first man steps his foot on surface of Mars. And long story short, the solution for that is to create an artificial gravity environment using the rotation of the habitat. This can be done in low Earth orbit, so you don't need to go to Mars to figure this out. And the result of this experiment can be twofold. Either we know that Moon or Mars gravity is good enough for any future colonists in space, and therefore we don't really need artificial gravity, and we can just go and proceed straight from Martian colonizations, or we see that 1g gravity is the lowest possible level, or some level of gravity which is above 1 on Mars is required for healthy development of human beings, and therefore all the Martian colonies would need such an environment as close to them as possible. And this is why they will need an orbital space station in Martian orbit with these conditions. So, to summarize the reason why we want to have this development done, it removes another risk factor. You don't want to build your interplanetary colony on assumptions and maybe it will work. You want to know a definite answer. What will work, what will not work. Let's talk about power on Mars. Power is the lifeblood of any human activity. But Mars is a very energy poor planet. There is no availability of any hydrocarbons that we know of. The surface of Mars is completely oxidized. There is no way to extract energy from what you can find on it. Most of the stuff is just, ash, metal oxides, CO2 and water. There is no flow in water on Mars, so there is no possibility to create a hydropower station. The atmosphere is very thin and dusty, and that makes it a problem both for the wind power, which is barely available, and even for the solar power, the only remaining source of energy on Mars. That's the problem. We probably can find things like uranium or thorium from the basic geochemistry considerations. They should be somewhere, but we don't know where. So what's the solution for that? If you look at the energy availability on Martian surface and optimal orbit for solar power collection, Sun synchronous orbit, the difference in raw energy is not that big. 100 watts per square meter versus 162 watts. But if you combine that with the lack of dust and atmosphere, with the fact that you can collect the power 24/7 in orbit, and many other smaller but important considerations, like dust storms can sometimes block entirely all the solar energy, you can see that the power in Martian orbit is a much better opportunity. So we can build our colony in orbit with the expectation of reliable source of energy there. One of the first questions for the Martian colonists is what am I going to eat? Every day there is a need for food for every single person on Mars. And there is important difference between the environments within Moon or low Earth orbit and deeper space. If you want to send a resupply ship to Moon or any orbit between Earth and Moon, there are no limitation where and how frequently you want to send those ships. There are no transit windows. You can send them as fast or as frequently as you want. On Mars, however, all the logistics is built around transit windows. Every couple of years there is an opportunity to send cargo to Mars, and if anything happens within that transport convoy or anything happens between those windows, immediate problem the colonists will have to deal with is starvation. Therefore, local food is incredibly important to make in place, to produce. In Martian orbit, as you know from the previous video, there is plenty of energy, much more than on Martian surface, but none of the ingredients that agriculture needs. Now, we know from the previous missions to Mars that Martian regolith, while not immediately useful soil, has all the ingredients for agricultural needs in any case. Some more rare than the other ones, but in principle you can extract them from the regolith and produce required nutrients for all the plants. And with the agriculture, you can build simple things first and more complex food chain later. Now, nitrogen, for example, has to be scavenged from the Martian atmosphere, which is quite a dilute source, but the short answer, we have all the ingredients. The only challenge to solve is the difference between energy availability in orbit and scarcity of resources, and abundance of resources needed for agriculture and scarcity of solar energy. But agriculture on Mars is possible, and this should be one of the first things that any Martian colony would need to set up. And I will cover more about resource constraints in our next video. Hello, let's talk about resource availability. For our civilization on Earth or on Mars, we need a lot of different types of raw building blocks. If we exclude hydrocarbons from the equation, we still need to have all the metals, water, silica for solar panels and electronics, many different alloys we're using, and all of that we need on Mars. So let's look at the availability and the costs. The delta V number means what velocity do we need to reach the specific destination from the origin. So for Mars surface, we need about 4 kilometers per second to reach Martian orbit. And if we need to transfer between Martian orbit and Martian satellites, we have a delta V of 1.3 to 1.8. This number directly translates to the energy cost. How much propellant do we need to ship those resources to specific destinations? And Earth, of course, have everything in abundance. However, it has the highest delta V cost. This is why utilizing local resources will be incredibly important to start as early as possible. Now, we have some understanding of what is available on each of the bodies. For example, lighter elements like water, oxygen and hydrogen, carbon dioxide, nitrogen, iron and aluminum are fairly abundant on Mars and in satellites. However, heavier elements like copper or tungsten or many other specialty metals, they are probably there, but we don't know where exactly. So as I mentioned before, we don't know where uranium mines, uranium ores are, so we have to do quite a lot of field geology to understand that. Now, in orbit, as I mentioned before, we have a lot more solar power available. So that can be an option to start our industrial base as well, as any kind of processing will require a lot of energy. So it is not just agriculture, but also initial industrial base can be also started in orbit. And when shipping from Earth, it's not that much different if we ship to Martian orbit or to Martian surface. Of course, we don't need to limit ourselves to just one option, but my point is that Martian orbit has both Martian satellites as potential resource bases, and we can still ship the stuff back and forth to the bases on the surface of the Mars. I will tell more about the plan how to build that industry using all the options available in the best possible manner in one of my next videos. In the meanwhile, you can just like and subscribe to my channel. The next challenge after mastering resource extraction would be building industrial base for our Martian colony. Now, if we are building full independent civilization, we need to scale our existing solutions to the right size for the size of our settlement. If you look at all the factories that we have on Earth, like steel smelting, or production of cars or other industrial equipment, they all can scale down reasonably well, down to the size we need. And I suggest the dimension of our microfactory will be similar to intermodal shipping container for the early stages. Some are easier to scale down, like machine working or food processing. Some are more difficult, like advanced pharmaceuticals or metal smelting. And some at the moment are impossible to scale down to the right size. This sector is semiconductors. It's really a big challenge to scale down a semiconductors fab to the size of the shipping container. However, this challenge is not impossible. While we cannot build an advanced CPU from the facilities we can fit in the small size, we can still build electronics using previous generations of technology. We don't need advanced computers on day one, but locally manufactured radios for the Martian colonists would be incredibly useful. And the major challenge is to find the right substitute that can be manufactured with limited capabilities, such as alternatives to transistor, be it vacuum tube or more exotic solution like superconducting junction or magnetic amplifiers. In any case, we will have something as a starting point using the capabilities that can be fit in a small lab. Those capabilities would be enough to start the electronic industry on Mars, and that's pretty much the biggest bottleneck we need to solve when scaling down industry sectors. Alright, you can like and subscribe this video, and there will be more to come. Before the first human will set their foot on surface of Mars, we would definitely need to deploy a considerable amount of unmanned assets, satellites and probes, to help our colonists navigate, map, and build on Mars. So if you look what's in orbit around Earth, we can use the same type of satellites to assist with the technology needs on Mars. On the synchronous orbit, high above Mars, we can place some communication satellites and meteorology ones, the same type we use in geosynchronous orbit around Earth, and we don't need a lot of them. Those would be handy for the early attempts when we need some communications delay with Earth and other orbital assets, and some weather forecasting on Mars. We want to know when there will be next dust storm, for example. The second and one of the most important one is a global navigation system for Martian explorers and colonists. As you may know, there is no magnetic field on Mars, so compass wouldn't work. So you need an equivalent of GPS in orbit around Mars before the first team, get lost in the desert. So they would need some navigation means. That would be medium Martian orbit, about 10,000 kilometers around Mars, similar to GPS constellation on Earth. As we get more people and we will have more communication and other needs that would require connectivity, we would also benefit from satellite internet similar to Starlink. That would require hundreds of satellites, unlike say GPS equivalent, which can do with 24, maybe even thousands. But that would give our every explorer an equivalent of Starlink internet connectivity on Mars. And when we do our initial reconnaissance, we would need some geological and mineralogical understanding. Where do we set our colonies? Where do we build our mines? And where do we search for things like uranium or other ores? That can be done with very low satellites that will skim the Martian atmosphere, and plenty of other, probes, landers and rovers that we already placed on Mars can be replicated as a fleet of explorers that would search interesting points on the surface on Mars. We would need more than one, but we'll definitely don't need 100 of them during the first stages, but we need some of them. So that would be unmanned assets that has to be moved in before we place the first manned crew on the surface of Mars, on the surface of Mars. That would be the unmanned assets that we need to place in orbit and on surface on Mars before we send there the first human crew. Now, let's imagine how our colonization program would proceed in multiple stages. So first of all, we want to deploy a forward operating base. Similar to Lunar Gateway, we can place it in orbit high enough above Mars, so we can easily access both the satellites and the Martian surface. Something like aerosynchronous orbit, similar to geosynchronous orbit on Earth, would be one such location. Once we have that outpost established, we would need to set up self-sufficiency capabilities as early as possible. While we will not be able to build industrial base in orbit quickly, we can still push the agriculture in space direction and build at least the base for the food security. The second direction is deploying the small surface outposts, seeking the locations of uranium ore, for example, or other energy opportunities, or will be the spot where we will build our industrial base. However, that requires actually, sending people and drilling the Martian ground. So that would take some time before we can build industrial and energy base on the surface of Mars. But once that's in place, we can expand both of the areas, both in orbit, building more agricultural facilities, orbital farms, recreation and other industry that can use resources from Martian satellites that will be low in delta-v costs, while the surface of Mars will become the base of most of our heavy industry, mining, energy, metal smelting, and we can rotate the population between the orbital and surface locations, exploiting the advantages of both and also relieving the crew from enduring Martian gravity
for extended period of times. So that's a very much an approximation, a draft. There are different possible directions we can take. For example, we can deploy our colonies on orbit first and build the orbital segment from ground up. Again, there are many options that can be considered, discussed, trade studies can be done. But that's a basic outline. Please like and subscribe our video, share in the social network, and leave comments on the YouTube. Hello everyone, and in this video I want to explain a little bit how the training and preparation can go. As you can see on Earth, our starting point, we can select our future colonies and give them some basic training, but the real preparations start in actual space. The best way to train someone to be an astronaut is to do it in the real environment. So in low Earth orbit, using our large space station design, we can test a lot of things, both in terms of technology and training the crews, like orbital farming, in-space operations and assembly, and getting the results from artificial gravity lab. Going beyond low Earth orbit and making our next boot camp on Moon, there are a lot more options that you can do in the deep space, radiation shielding and more advanced mining and manufacturing technologies. But you're also close enough to Earth so that any necessary supply or any assistance can come as quickly as possible in the matter of days. And in this way you build a body of knowledge, you build a large number of trained people, making them ready for the final step, where they can start building the full colony on Mars with already some experience in operations in low Earth orbit, Moon, and with all or most of the technologies already debugged to the point they can work reliably on Moon, as we used our previous steps to gain this valuable experience. Now, this is just a short summary, an overview, and I will come back to other areas like social institutions on another planet, or nation building on another planet in my next videos. Please like and subscribe. Thank you. If we look at the different orbital environments, low Earth orbit, Martian orbit, lunar orbit, we can see that the parameters of these environments, from distance to Earth to solar power level to radiation levels, gradually grow from easier to harder. And if we are going to build solutions that are going to work in Martian orbit, we can absolutely use lunar orbit or low Earth orbit to develop and debug them, and that difficulty curve allows us to understand all the challenges that will be required to build an orbital settlement, an orbital outpost in orbit around Mars over iterations at the destinations that are closer to Earth, such as lunar orbit or low Earth orbit. Now, if you look at the surface environments on Earth, Moon, and Mars, you can immediately see the differences between the three. And of course, the gravity is different, the atmosphere is completely absent on the Moon and barely present on Mars. There is almost no water on the Moon, and there is some on Mars, and of course, solar power we have discussed before. It's good on Earth, even better on Moon, and somewhat more difficult to get on Mars. Now, the point of that, if we are going to use Moon to train our Martian explorers, Moon is actually harsher environment, and it is going to be useful for our future settlers because you have to train harder than you fight. And this is why Moon as a boot camp for Martian settlers is incredibly useful, and it is wise not to skip it in the process of building our Martian colony. There will be 3 waves of settlers, colonists, each with specific goals and each time roughly an order of magnitude larger than the previous one. The first one will be the scouts, highly trained specialists that will be investigating the best spots for larger colonies, larger settlements. They will be doing geology and all initial scouting of the area. The second step will be builders. There will be more of them. For 100 of scouts, we can expect 1,000 of builders. They will focus on creating all the infrastructure for energy and agriculture first and foremost, and also enabling that infrastructure to support larger number of colonists. And the final and the biggest wave will be the actual settlers. They might not be astronauts or trained in the specifics of Martian exploration, but they will have all the possible occupations that future Martian colony will need, from doctors to artists. And of course, there will be a lot more of them in tens of thousands, creating the foundation for the true interplanetary civilization on Mars. The first thing that first groups of colonists would need to find are the resources: water, ores, metals, other materials. We don't know enough about Martian geology to pinpoint those locations, but we know enough where approximately those places are. Water is available as subsurface ice in high latitudes, and metals and other ores are usually associated with mountains, volcanism, and sometimes with secondary deposits by water or wind erosion. Now, if we look at the first sites suggested by SpaceX, we can see that those are in the flat areas with the reason why, because landing sites have to be below surface, below certain level of atmosphere, certain thickness of atmosphere, has to be flat and low on rocky areas. These sites are close to water deposits. They're high enough in terms of water availability, but they're pretty far away from everything else. So in the first thing, our future colonists would also need a way to transport their reconnaissance activities across quite a large area. And we will talk about that in the later videos. But right now, the first thing to secure would be power and proximity to ice for the first settlement on Mars. The first thing that our first scouts would do is field geology. They have to find all the places where the potential minerals, ores, any resources are for both industry and agriculture. That means a lot of exploration. What options do they have for transport across Martian surface? Of course, they can do everything on foot. You can get anywhere, but you're limited in terms of payload and range you can get. A better option, use the rovers, like scaled up Spirit, Opportunity, or Curiosity. They can get farther and faster and then can carry a lot more. Of course, you would need a power source to recharge them, and they can't actually go anywhere that humans can do. There's still some terrain limits. But there's also one more option that scouts, Martian scouts, should consider. This option is called Hopper, vertical takeoff, vertical landing rocket, with the capability to land pretty much anywhere and much longer range. It provides an opportunity to cover a much larger distance, and I'll show you this on the next slide. If you look at the potential landing site, Arcadia Planitia, and I market the ranges that people can cover on foot, roughly 10 kilometers, 10 out, 10 back, and 10 around, so 30 kilometers with 30 kilogram payload. That's a small green circle. You see how small it is. Rover, the maximum safe range would be around 42 kilometers. That's not necessarily the limitation for the rover. but in case of breakdown, the crew should be able to walk back on foot within the range of the oxygen supply. I would set that limit at 42 kilometers. You can walk that within 8 hours or so. Now the hopper can both ascend, land, and return in much longer range, around 150 kilometers, with sufficient fuel reserves. And two bases separated by several hundred kilometers can be connected by those hopper flights as long as you can refuel it at each spot. And the large dotted red circle is actual range that a hopper can cover in the center of Arcadia Planitia. So pretty much every spot there can be covered by the hopper flight. If there are two bases anywhere within this big red circle, you can establish transportation network within this range. And it is very important that you have access to orbit in emergency. For example, if you need to escape and your spaceship, Starship, is available in orbit, so the hopper is designed with orbital ascent capability in mind as well. Let's talk about power challenge on Mars. If we want to rely our settlement on solar power alone, there is quite a lot of demand for both life support, production of food, or propellant production. At the very bare minimum, you would need something like 300,000 square meters of solar panel, and that's like 3,000 tons or plus 300 tons of batteries. And that would work, of course, but you would need something else to back up your solar power. Opportunity worked for 14 years on solar power backed by battery, but one day the solar storm was just too big and it was not enough. Now imagine the same fate for the colony that you don't want to happen. Nuclear is really the only other available option on another planet that has no fossil fuel or wind power or any other sources of energy. You can use different scale for different type of solutions. RTG, radioactive isotope generators, can support your communication system indefinitely, and they will not rely on solar power during the dust storms. A small-scale microreactor like Kilopower from NASA can provide enough energy to recharge your batteries during the low power conditions or blackouts, or support your environmental support system. They don't also have a lot of mass to transfer, so from 100 kilograms to a few tons at most. Of course, they would need nuclear fuel and all the regulatory approvals, but that happens on Earth. And if we go on the higher end, we can also rely on our nuclear reactors for industrial needs. Small modular reactors have from 5 to 300 megawatt electric power that can cover all our base needs and provide a robust base for a Martian colony in the foreseeable future. You would need to find uranium on Mars to make them work indefinitely, but the good news, there is uranium on Mars somewhere. Let's talk a bit about navigation on Mars. You don't want to get lost on another planet with no air to breathe outside your spacesuit. So what we use on Earth today on aircraft, ships, cars is GPS, GNSS, Global Navigation System, and Inertial Navigation System as gold standard. Now we can absolutely build the satellite constellation on Mars and use it in the same way on Mars as well. However, it would be good to have some fallback options. What happens if your Martian GPS is down? What happens if you don't have your hardware in place when you are already somewhere lost on Mars? So 4 basic things, how we used to do navigation before GPS. We need to get direction. Gyro compass can do. It will work on Mars just as well as it will work on Earth, because there's no magnetic field on Mars, but there is gravity, you can still use gyro compass in the same way you would use on Earth. You can use sextant and chronometer, accurate watch, plus a map to get your latitude, longitude with reasonable degree of accuracy. And what's good, this is fairly low-cost solutions. It's not gonna cost a lot of money, and they will work without any additional means, sometimes without even any extra power sources. Our best historical approximation to Martian exploration comes from the age of polar exploration in the early 20th century, late 19th century. At the time, it was done at the age of technology, and the distance was large enough so that travel took months. The environment was hostile, the local resources were scarce. Team size and composition would be close approximation to what we can expect from first Martian expeditions, scientists, military, and professionals. And the expedition length was pretty similar. If we're talking about end to end, it was on average about 2 years, and with casualties in a single-digit percentage overall for the entire duration of this period. Now, a lot of them were quite successful, with 0 people dying, but a lot of them were fairly difficult and sometimes catastrophic, like Franklin's last expedition. So we need to learn lessons from those events. What to do, what not to do. And the most common lessons is basically very obvious, but maybe not so obvious when you try to do things anew. Use proven technology, use trained people, include redundancy and backups for all your solutions, and of course, get the best possible leadership. And in many of those cases where things went, sideways or completely wrong, people expected things to be too good to be true, and it was not the case. They relied too much on the experimental, unproven technological solutions, be it the Robert Scott motor sledges or, Swedish explorer air balloon. It was not good enough and was never tested in the environment expected. And don't pick up the, people who are enthusiastic but lack necessary skills and experience. Mars is a very difficult environment. Logistics is incredibly difficult for any Martian expedition. Even at the edge, at the bleeding edge of our technology, it would be very difficult. It would be a very difficult adventure, and what's important, a very long one. Even two-way expeditions are expected to last 3 years. 3 years of very difficult environment, a lot of challenges, and what's important, it's not just people, it's not just technology, it's people who can wear out, crumble, and die, and you don't want this to happen on the surface of another planet, with millions of kilometers away from any help. Let's estimate the timelines for Starship development and first expeditions to Mars. So between 2026 and 2038, there are a few transit windows that we can use. Of course, we don't need to launch people on the first spacecraft to Mars. We need to qualify it on cargo flights, deploying satellites and other stuff to the orbit and surface. And then once we have confidence in the ability to deliver people safely to the surface on Mars, we can use the next transit windows. So if you look at the slide, you can probably see that the first few opportunities will be used for cargo only, and once we have that capability, we can start sending people. Orbit is, easier target to reach. You don't need re-entry, so we can launch first ships without needing to land them on Mars. But after the orbit, delivery is done, we can launch people and supplies to the surface. So, long story short, there will be first people on Mars probably by 2023 at the earliest. A few words on communication for the Martian expedition and Earth. Mars is quite far away in terms of distance, and furthermore, sometimes during the conjunction events, Mars is directly behind the Sun, and communication is just not possible. So all the planet activities, all the planet actions by the expedition members have to rely on the fact that they will be fully autonomous, and of course advice from Earth can come, but it will be minutes away, not seconds, unlike Apollo missions. And we need additional infrastructure either at L4, Lagrange point, or L5 for a relay satellite that can cover the conjunction timeframes. Again, nothing is a showstopper, but we need to account for those factors for our future Martian exploration. Imagine you are on Mars. What would be the immediate, most urgent need you will experience? The need to breathe. There is no breathable atmosphere on Mars, so the first and most important piece of equipment is a spacesuit. It should be different from currently used on ISS or other spacecraft. It should be suitable for daily activity outside the pressurized environment, should have sufficient life support for 8 hours of workday and up to a day, full day for emergency needs, and should be durable amounts for entire duration of the Martian expedition, which may take many months. The second thing, after you spend a day in the spacesuit, you want to find a spot to take it off, and that would be the basic shelter. Again, nothing that has been done before on any other, celestial body, so it has to be designed with the capability to be operational for entire duration of Martian expedition, designed to protect against radiation and micrometeoroids, and comfortable for 24/7 habitation. None of those requirements are impossible to meet, but they're important to be understood for any future Martian explorer. There is one more thing that's important for all the future Martian expeditions. Whatever they do, and no matter how long they stay, they should the consumables, water, air, food, and power available in abundance, even overabundance, 3 times or 10 times what they plan to consume. Because until they establish their own facilities for life support, food production, power stations, they will be highly dependent on what's available with them because there is nothing on Mars. That's why redundancy and over-provision is supremely important for the first Martian expeditions. The next step after initial scouting expeditions, is to send a lot more people to actually build all the infrastructure we need. If scouting can be done by professional astronaut corps, building all the infrastructure will take a lot more people than all the astronauts we have on Earth. So we need to create a selection pipeline, select a lot of candidates, check them for health and intelligence, other capabilities, and create a funnel where we select best of the best through training, through team building, through exercises on Earth and in space. And in this way, we can select enough people of the right kind to build the next step of the Martian colony. Now let's talk about training. If you look at the geometry of the Martian orbit, we have transit windows available every 26 months. That means you have 26 months to prepare the next batch of colonists. And some of the things you see are kind of staring in your face. If you want to train people for space operations, the best place to do that in space. If you want to train people for any orbital skills, in-orbit skills like refueling or docking, these are best done in space. Same thing for surface operation. The second best place to prepare people for Martian base operation is lunar base. So if you look at the training program, it can start with theory and ground exercise, but the final months and weeks should be absolutely done in space. So the first boot camp can be done in low Earth orbit, up to 1 month at International Space Station or dedicated space station for Martian colonists training. And the second boot camp can be done on surface of the moon, so people gain experience working and living on another celestial body, and that would be the best possible program. So by the time they reach Mars, they have at least some spaceflight experience. If the first scouting expeditions can be done by trained astronauts, building up Mars will require thousands of people, and before you send them to another planet, you have to train them in the environment that will most closely match the challenges that they will face. That means another location in space, be it low Earth orbit or moon. Well, after building up the small base camp, the next expeditions will focus on building up the bigger base. Here is an overview of such base. It's large enough for, a lot more people, tens of them, comfortable enough so they can live there for many years, and also safe enough against all environmental hazards, radiation, external, atmosphere, meteorites. In addition, power is everything on Mars. There's no other option than to have multiple redundant sources in addition to solar power, be it nuclear, and most likely nothing else would work, because power powers everything. The life support, the agriculture, communications, transportation, in situ resource mining, everything depends on available power. Now this base would be good enough for long-term living, but also the second most important part after the power is agriculture. We should also provide enough locally produced food for the builders of the Martian infrastructure, and food can be, farms and greenhouses in the compact, vertical design with both, agricultural produce and animal farms, fish is possible within the, relatively small volume. However, it also depends on power. If we want to produce anything on Mars relying on just, solar irradiation, that would be not enough, because solar power is much less available on Mars, and therefore we need to augment it with artificial light. So power, and more power. That's a necessary element for not just survival, but for thriving on Mars. The second half of the Martian colony will be in orbit. You have to think of the place to explore and colonize not as just the surface of the Mars, but the entire volume from the surface all the way to Martian satellites as one continuous place to inhabit. That will allow access to much better environment for the solar power. That would allow also capability to develop asteroid mining and artificial gravity technology that would be useful for the Martian colonists. And what is more important, if space becomes an everyday utility for the Martian inhabitants, Martian culture will become a spacefaring one in the same way that we have, maritime cultures on Earth. And there's no limit to how far the future generations of Martian colonists will expand beyond their home planet. Let's talk about Martian supply chain. If we look at what we need for the Martian colonies to build, we need a lot of supplies that can be either transferred from Earth or manufactured in place, called in situ resource mining. So what can we build on Mars? What can we create using just materials that are widely abundant on Mars? Those are carbon dioxide, water, nitrogen, and other light elements like chlorine and sulfur. So if you have energy, you can kind of convert one into another. And if you look at the slide, you can see the whole chain starting from water and carbon dioxide. You can get methane. With methane, you get more and more advanced chemicals using only energy, heat, and all the other components you can get from the original inputs. And if you continue, you can see that you can manufacture things like fertilizers, explosives, components for organic synthesis, everything pretty much you need in organic chemistry, and all the way down to polymers like polyethylene and polystyrene. Now, if you roll all the way back to the original slide, you can see very important addition on the bottom: catalysts and solvents not shown. That means that the actual bottlenecks for in situ resource production are not the input elements like water and carbon dioxide. Those we have in abundance. Things we actually need and we cannot manufacture them on Mars on day one are the catalysts, which are fairly exotic, can be fairly exotic compounds. We'll need relatively rare metals like ruthenium or platinum group metals, and energy. Everywhere you see the reactions, you will need either electricity for electrolysis, or high pressure and high temperature to accelerate the reactions, and so on. Those are the real bottlenecks: power, electricity, and the catalysts, and some solvents. But solvents you can probably make it in place. The catalysts you have to import for a very long time from Earth. Let's talk about metallurgy on Mars. For anything other than base metals like iron or aluminum, we don't know exact locations of the ores. Where lead or copper concentrations are located, we have only some approximate idea. It's all doable in terms of we can find and start, digging for the ore, but it still has to be done. Another thing that has to be addressed when doing anything metallurgical on Mars is the lack of any reducing agents available immediately. You need either hydrogen or carbon monoxide or electricity to smelt any metal pretty much from oxides, carbonates. For some things, some of them it's relatively straightforward. For some of them, a more advanced chemistry is required. For aluminum, for example, you can't just electrolyze alumina. You have to first dissolve it into the cryolite fluoride mineral, which lowers the melting point of the electrolysis process. And that you have to be either manufacturing on Mars or importing from Earth. If we go into more sophisticated alloys, we would need a lot of extra metals like molybdenum or tungsten or lithium or magnesium, and all of them require quite a lot of field geology to discover the deposits. And just as with previous metals, you need reducing agents like electricity or carbon or hydrogen to extract the ore to extract the metal from the ore. For titanium, for example, you need to reduce it with magnesium, and magnesium you have to reduce it with its own process, usually electricity.
So all of this presents a long list of challenges. None of them are fundamentally, unsolvable, but all of them require thorough, detailed solution, starting with locating the ore deposits, and developing the Mars-specific metallurgical process, which takes into account availability or lack of specific chemicals, resources, or environment conditions. Let's talk about the next step, manufacturing on Mars. If we have a CNC machine on Earth or on Mars, you can use it to make stuff. But the question is, to bootstrap the manufacturing capability on Mars, you need to make a CNC machine using the resources and skills you have available on another planet only. And if you look, you can see, of course, the metal structure, actuators, cabling, electric and signals, power and signals, hydraulics, other stuff, cutting tools, electronics and software are also important parts. And all of that has to exist on Mars before you build the first CNC machine. In our next videos, we'll cover all of those areas separately. But think of this task as a benchmark to understand what is required to create an independent manufacturing capability on another planet. Let's continue reviewing the requirements for developing indigenous manufacturing capability. For a CNC machine, you also need cutting tools, and cutting tools are usually ceramics. And if you look at the availability on Mars, you can see that common oxides like silica or alumina are fairly common on Mars, but more specialized compounds like rare earth oxides or tungsten carbide, which you need for the cutting tool, they are a lot more scarce. Just like on Earth, you need to find the source for the tungsten ore, do all the processing, sinter it with cobalt, and so on. So ceramics are another dependency in the supply chain. You need to understand, develop, do the field geology, and create the independent manufacturing capability to make those materials. And I don't even mention the processing part, which includes quite advanced, melting and sintering the ceramics with a laser or high temperature. Continuing with the prerequisites to make indigenous CNC machine, you also have to think of the electronics you can build on Mars, be it day 1 or be it year 20. And if you look at the history of terrestrial industry, you can see that vacuum tubes can be manufactured relatively simple in a glass blower lab. But once you go into the semiconductors, it will require many decades to make even single transistor reliably, and integrated circuits or advanced ACs will take even more time. However, do not despair. You can make a digital computer with just vacuum tubes. You can make a PID controller with just vacuum tubes. So it might be possible to make the manufacturing capability on Mars using just basic electronics. You can make a basic radio, you can make a radar, you can make quite a lot of advanced electronics using just vacuum tubes. Of course, they will be more, bulky, will consume more power, and will be less reliable than semiconductors, but they will work, and this is something that should be considered for the Martian colony development. In the next video, we'll cover more advanced technologies like software and pharmaceuticals, and we can show that while we cannot replicate the entire Earth supply chain and capabilities, we can make just enough of them that will be sufficient for the first years of Martian colony development. Let's talk about building software on Mars. What do you need not just to use any kind of software tools, but to build your own? Of course, you need actual computers, but in terms of other software available immediately at your screen, you need also operating system, you need software libraries,
you need compilers for the programming languages, you need a version control system like Git, and of course you need editing environment like Vim or Visual Studio. And once you are done, you need to distribute your software through FTP or HTTP or any other media. Now, all of that has to be physically present on another planet. You can't just rely on Earth Internet to deliver your software libraries or packages to Mars, because the delay due to distance is measured in many minutes, and you don't want to be depending on the Earth software in case of any outage and you cannot fix it and you need it on Mars. So the bottom line, you need to create your own internet, you need to create your own content delivery, and you need to have a library of all the software you will need on Mars on day one when you start your colony on another planet. We'll talk more about other underlying technologies in the next videos, but this is one of those things that if it works, then people take it as granted, but if it doesn't work, then you can't really do nothing. You can't really do anything if you don't have all those tools available. Pharmaceuticals. If we want to set up a base of operation on Mars, we want to also have all the capabilities for drugs and medicine available as early as possible. While things like aspirin or basic antiseptics can be synthesized from hydrocarbons fairly quickly, if you look at the aspirin structure on the left of the slide, the more you go into more advanced pharmaceuticals, the more difficult it becomes. So it makes sense to stage your development of your pharmaceutical industry on Mars in a similar way, in iterations, first started with simple components and get into the more complex one. If you look at the things like monoclonal antibodies, and that's the structure on the right, you can see how complex those drugs can get with thousands of atoms in precise configuration, and it's not just feasible to have those independent manufacturing capabilities on day one. So you start with basic, scale up, and get into the more complex medications later on. There is also a good, useful benchmark published by a World Health Organization called Essential Medical List. And if you look at those drugs, if you can synthesize them in place, you are already 90% covered for all the needs of your healthcare and medication production. Now, for our next video, let's talk about timekeeping on Mars. As many people already know, Martian day, called Sol, is almost equal to Earth day, about 24 hours plus some extra minutes. So it's relatively easy to design a clock for Mars. You can just make the second a little bit longer, so you have 24 hours, 60 minutes, and 60 slightly longer seconds. And you design and adapt our software to Martian version of it, such as NTP and PTP protocols. However, there's one thing missing at the moment, which is called time zones. As we have time zones on Earth, we should also have time zones for Mars. And on the picture you can see like approximately how they would look like. 24 time zones, each 15 degrees long, will form the entire circumference of 360 degrees. And the time will be off by 1 hour in each of the time zones. So you get like +1, +2, -1, -2, and so on, just like we have on Earth. It's not a difficult thing to do this, but it's also something that has to be done and works reliably and agreed by all the parties who will ever settle Mars, so the people in different locations have their clock and time zone exactly as expected. And operating any complex mission would require precise timekeeping. And one more thing, which is also very important, is to have a proper Martian calendar, but we'll talk about that in our next video.